I believe I will probably need some more light in here, won't I? Well, this is a new class today, ECGR 4101, 5101, and we just had a quiz, and so there's a lot of happy people in this room and a lot of sad people in this room. But my goal is to make sure that we cover everything that we should cover, and I got to make sure to turn all my notes out. We're going to start now with, should be chapter number 3. For those of you who have, here, ECGR 4101, 5101, ELET 4133, lecture 7, page number 1. The discussion for this is microcontrollers in general. Now, this is where some of you will have to go to sleep. Organization of and architecture of the Renesas microcontroller board. I will have to admit that a lot of you from engineering technology have probably had this already. I am looking for the light switches for here. Since I use both the screen up there and the board, I'm going to turn it up full. So, what I need to point out is the following. If we're looking at a microcontroller, what is the true definition of a microcontroller?
A microprocessor with peripherals?
It's micro, I like that. Yes, it is micro.
Microprocessor with peripherals?
It's got a microprocessor and microprocessor functionality. I am looking, oh, there's my notes, finally. What else?
Timers, input, output,
Speak loud. I have somebody talking over here and I can't hear.
Timers.
All right, timers.
ADC.
ADC, a whole bunch of little additional stuff, right?
Yeah.
All right, so let's step back right now and let's just look at a microprocessor architecture. Now I'm going to go back to your digital logic classes and also your computer architecture classes for this. What you will typically see is two general parts of an architecture. You'll have your data path and you'll have your control path. And the control path will literally control what the data path does. Think about this. When you're running a program, which part of this microprocessor architecture is taking the instructions? The control path, right? It is that which takes and decodes your instruction. This is already covered in computer architecture, so I'm not going on and doing that. And I think you ET guys, you've already had this already, right? Yes? No? Okay. And the data path. Where is that information coming from and going to?
Memory.
All right, I heard several things, so I'll start off and say, one person said registers. That is correct. There's also some place you can come to and go to. I think I heard it over here. Memory. I think one of you guys said that, right? And what was the other one?
Input, output.
Input, output, no, devices. So, notice that what's going on here. There is a possibility for you to have some memory over here, which is actually program memory. And the program memory will be used to feed the control path. Now what you'll see here is in a microcontroller, this will mostly be flash or some other type of semi-permanent memory. And in a regular microprocessor environment like a PC, you'll mostly see this in RAM. Because there's a hierarchy of memory for the program that could come from disk, for example, and then get loaded into RAM and then run. So if you're thinking about data, oh, by the way, and typically, do you send anything into the program memory in normal operation? No. In fact, that's one thing that's usually very bad. What we call self-modifying code is where a microcontroller, microprocessor will actually change its own code. You know what? I should probably turn this on. And so in data path, what will you have? Well, you'll also have some memory over here, right? And this is data memory. And do you write to and from data memory in the data path part? Oh yeah, you do. All right. And this is usually RAM. Sometimes in rare cases, it might be double EEPROM. Double EEPROM, remember what is that called?
Electrically erasable programmable.
Right, electrically erasable, programmable, read-only memory. But very often we use it in a microcontroller for a way to easily change a single byte of data, and then when the machine powers off and you power it back on, well then that data is still stored in that memory. And that might be something that's very important. Like, give you a good idea, the settings for a phone is a good example. You don't want that to go away when you power the phone off. Or, for that matter, the settings of any of your devices that you might have that you want to keep the configuration data in there. It could also be stored in other ways, but this is just an example. Now, depending on the sophistication of your device, sometimes this shares the same space. But in an embedded system, typically you're going to see these completely separate. This will be flash, this will be RAM. And also depending on the sophistication of your devices, you may have something called a memory protection unit. Or a memory management unit. And in the case of our system here, in our board, we really don't have a memory management unit, but I believe it is built onto the chip. Memory management is especially useful if you want to pretend you have a lot more memory space than you actually have, and then you write extra stuff off to your hard drive. In other words, a memory management unit is needed when you have different levels of memory. Anybody familiar with the term cache?
Yes.
And of course, hard disk space. So in your PC, you typically have cache, which is data that's faster than your regular RAM. And then you have hard drive, which is slower than your memory RAM. And you need these pieces of hardware that will handle how data is moved from disk to memory, main memory to cache. Cache is, as I said, much faster than regular RAM, and your modern PCs usually have lots of it. Like you've probably seen L2 cache, level 2 cache. So that's just a little background of microprocessor architecture and where the embedded system or your typical microcontroller will fit into this. Historically, microcontrollers didn't have MMUs, but they're more and more are getting them because they're 32-bit microcontrollers, as opposed to the old 8-bit, like an Atmel. An Atmel is a tiny little processor that can't handle very many things nowadays because everybody wants a lot more functionality. So, let's take a look at the Renesas RX62N. And by the way, there is going to be a phasing out of this processor, and it is going to the RX63N. And this device, the RX63N, has even more flash memory and RAM and such like that. In fact, did I show you the small little pink board a couple of weeks ago? Looked like a Arduino.
Yeah.
That was a 63N processor that the boards will actually start to come out this fall. I'm trying to remember when. And if I have enough time, I may have the graduate students work on that. Or I may have them do some other projects. I'm not sure what we're going to do yet. But I'm waiting for them to come in. So, let's take a look at some of the features. Data path. Data path is identified as how much? Good. Make sure to point out that to me all the time, because sometimes I forget. Data path is how wide? In other words, how many bits of data are transferred or used at any one time?
Depends on the controller we're using.
For our controller. All right, it's 32 bits.
Is it wide?
32 bits means our registers are 32 bits wide. We're moving data typically from memory 32 bits at a time. You can move it at 8 bits or 16 bits at a time, but it is capable of 32 bits. Oh, how fast does that go? I think it's at 100 megahertz, right? Well, that's kind of worthless, right? Because if you think about it, your typical Intel, whatever the current Intel family is, I mean, they change it every day, 2.6 gigahertz, right? But also keep in mind that 2.6 gigahertz microcontroller costs $100 versus these smaller ones, which cost about $7 or less. Now the question is, do you want to put a $100 microprocessor in your watch? No. All right. Do you want to put a $100 microprocessor in? I'm looking for a little worthless calculator. No. So there is a price point for all of your computing devices, and it turns out that this works very well for embedded system devices that cost maybe between $100 and $200. If it's less than that, if it's toys that cost maybe $10, then you'll go with, and you'll have less functionality with those, you'll go with a small little 8-bit processor that maybe runs at 4 to 20 megahertz and costs 50 cents each. Now, what kind of computation do our processors do? Do you think there's a lot of floating point calculation in a watch?
No.
No. Everything is pretty much integer. When you're counting up seconds, you're counting up 1, 2, 3. You're not counting up 0.15, 0.2, 0.25. So it's really integers that you're working with. So when you get into bigger microcontrollers and bigger processors, you will have a floating point unit. And there's a or as you add more functionality to the chip, it takes more space. So if you looked at your typical size of a microcontroller, not to scale, and let's say this is 2 millimeters. If you look at your typical device, this will be allocated to RAM, this will be allocated to your arithmetic logic unit, this might be allocated to your floating point unit, and this might be allocated to everything else. So RAM takes up your biggest amount of space. And I'll give some space over here for flash. RAM takes your biggest amount of space. Flash and other types of memories, a little bit less. Floating point is something that may or may not be needed, depending on what your application is. By the way, how much memory does our board have? This might be a good question for a future quiz. Suddenly I hear a lot of people say, "Oh crap!" All right, so how much RAM do we have? How much? 96? How do you know that? It's in where? Oh, it's in the book. You read the book? Oh, right, here. Take a trip to the prize plaza. All right. Are you embarrassed now? Yeah, okay. Sorry.
Yes.
Imagine all the people watching this out in the world. All right, how much flash is there in our device? This is our ROM, our read-only memory. You can answer that too, because it's probably on that page, right? All right, 512. Now, here's an interesting one. We're going to say data flash. Which acts like EEPROM. And that is going to be for how much? Remember what I said data flash is used for? For diagnostic, configuration, one thing we also use it for is debugging. So imagine this. I'm running a program on my new device that I'm designing, my cell phone. And I want to make sure that if something goes wrong, I have at least stored information of what was going on. In other words, what state was I in, what type of code was I running, etc. So maybe I will write off into my EEPROM or my data flash some additional information just as I'm about to reset my phone or my device I'm testing. So that would be another thing that you'll do in data flash. And the general address space is what? How many bits in our address space? An address is made up of how many bits? Give you a hint, it's really close to what the data path is. All right. So our address space is 2 to the 32 bytes, which is equal to 4 gigabytes. 4 billion something or other. In fact, how much is it? I love pulling up my calculator. Let's do that. calculator. There we go. Oh, I don't have permission. Oh, you know what I could have done? Somebody told me about this. On my calculator, if I turn it sideways, it turns into scientific mode. Somebody showed me that the other day. Did you know that? The iPhone. And I'll sell it to these people. I think, whoa, what the heck? All right, let's do this.
I'll take a TIE now.
Now everybody's going to pull their iPhone out. Utilities, calculator. So here's my wonderful calculator. So if I turn it sideways, look at that!
I think I'm doing it wrong.
Pardon me?
I think I'm doing it wrong.
That's an Android, man.
TI-89.
Oh, TI-89. Yeah, everybody's a comedian, aren't they? 2 raised to the 32 equals, ooh, it's 4,000, or 4,294,967, no. Yeah, 94 million. 4 gigs, all right? You know what a gig is, right? Good enough. Going on. So, we were also saying, what are the other little goodies inside? We said clock, right? Or no, you said timer, right? What else is inside? Say that again? Ooh, I like this. Analog to digital. Oh, digital to analog converters. Often called ADCs and DACs. Just so that you know what that is. And what other wonderful things do we have? Ooh, we have ports, which will be our input, output. But maybe I should say, in particular, what kind of input and output? Well, we have different types of things, like we have serial, right? So we'll see some sort of serial, UART, USART, some other type of communications port. I think we've already mentioned A to D, right? So we'll have A to D ports, or specific pins allocated to A to D. We'll have general digital input-output ports, which, by the way, some of these actually can be used for adding additional memory and addressing that memory later on. Let's see, what other functionalities do we have? Oh, I like this. DMA, direct memory access. This is where I mess up with somebody, right? So this is where I'm going to have. I'm going to bug somebody. Mr. Morgan, I haven't bugged you yet today, have I? Fine, bug. All right, I have it. All right, great. Your goal is to give to Mr. Wesley one of these pens. All right, one every 10 seconds. I need another pen. Let's see. All right, here. I'll use this one too. All right. Now think about this. Does anybody not know what DMA is? All right. Who knows what DMA is? So I'm going to call on somebody who's not, or who is raising their hand. All right. Or yeah. No, I'm not going to call it. All right. I'll just, since nobody knows what it is except for these two guys over here, which. You want to teach a class? I'm kind of tired today. You want to do that?
Tell what DMA is?
Yeah, no, I'll do it, all right. I'll do it with an example, all right? I'm going to continue this lecture, and this transferring of 6 pens between these two gentlemen is really something that's easy to do, and I can just have these two guys do it directly, right? But it's got to be one every 10 seconds, all right? So what I'm going to do is I'm going to pretend that I'm going to set up this direct transfer access, direct memory access. And I'm going to say, here's my setup. Here's all the data, transfer it to him. Go nuts. And as he's sitting there, handing it every 10 seconds, you have to figure out every 10 seconds, by the way. And then I can just go on and do whatever I want. Here's the nice thing, all right? Even though they're using a resource transferring between one person and the other, I haven't seen you oh, there we go. Even though he's using a resource, right, which is a memory link between the two people, or a link between the two people, I can keep on going, right? So, and I don't have to check with them. And what Mr. Morgan will do is when he's done with transferring all this stuff, he'll let me know. And the great thing is, I've now continued my lecture on like a processor, continuing other work. And I don't have to worry about this thing, which is the same thing every time. And. So, isn't this a great example of DMA? All right, there we go. Congrats. Have you had a trip to the prize closet yet? No. You want a trip to the prize closet? You have to stand in line after. Oh man, I thought I'd get a pen out of this too. All right. We're now actually going to go into DMA in this class. It is one of the classes for advanced embedded, but I thought it would be important to know about it, so that when we discuss it or that you're aware of it later, you'll know what that is. Oh, by the way, there's also one more thing that's really important, and that is reset circuitry. Eventually, you're going to have to say, I'm done, or something really happened bad here, and I want you to start all over from scratch. All right? Now, what's the main operation of a computer or a processor? What does a processor do? I like this. What does a processor do? Processes data. Do you like that? That's exactly what it does. In the processing of data, what does that mean exactly? What happens? There's operations, right? It does a lot of pluses and minuses and multiply by and divide by, right? Oh, it also does other things like, is A equal to B? And comparing and things like that, right? But one thing that you have to keep in mind is in our processor, a lot of what is going to go on, you need to keep track of. What are some of the things that you need to flag or to keep track of as a processor does its processing? I'd say the results of an operation. Well, it needs to let it know, was it 0? Did the operation result in a 0? Or did the operation result in a positive? Or did it result in a negative? Or did it result in an overflow? Who does not know what an overflow is? Good. I'm going to call on one person who did not raise their hand. So, this young lady in the aqua shirt. What does overflow mean?
When the contents of two registers are not in, so there's an overflow between. I don't know.
You were almost there. Just finish that thought.
Yeah, so when the capacity of the register exceeds the overflow resistance.
Okay, that's That's it. The capacity of the resulting register is not big enough for the operation. You add two numbers together that are really big, and the result doesn't fit in the one that's really big. That's an overflow. That's a trip to the price closet. She's like, yay, I get to have a man's hat. All right. And then what else do we have? How about carry? All of these are considered what major type of or where is all of this good information stored? Flags. And again, that is a basic computer organization type of topic. A flag, for example, in this example, is A equal to B, or maybe A minus B is equal to C. What's the result of that? Well, if it's 0, then you know that it's equal, right? So in this case, if you say A minus B, it will come up with the result C. You really don't need to look at what is C. All you need to say is it 0? Because that's what we're looking for up here. So very often all you have to do is do an arithmetic operation. But you're really worried about this 0 flag. By the way, all of these are stored in what's called a status word. So our status word has some wonderful information in it. Not only is it all the flags, but it is also information on the interrupt level. ET guys, have you had interrupts yet? Is that yes or no? Yes. All right. So, interrupt level. Not all people are created equal. For example, a full professor is more important than an associate professor, right? And an assistant professor is less important than an associate professor. So if you have an assistant professor sitting in a room, or teaching in a room, and he is the lowest priority, right? And a full professor comes in, the full professor has the right to say, assistant professor, sit down, I'm teaching now. And they'll come up and they'll teach for about 2 minutes and then they'll walk out of the room, right? That's an interrupt. The full professor, which has a higher priority level, can come in and basically take over what an assistant professor does. A full or very important process that has a high interrupt level can take over a microprocessor when a lower level process is going on. Same idea, all right? Except I did it with faculty members, which, I don't know, I think it's funny. Do you think it's funny? The other thing to worry about is what we call is interrupt level. So, I'm an associate professor. That means a full professor can come into this room and start teaching and basically tell me to sit down. How do I prevent that from happening?
Lock entrance.
Lock the door, exactly. So, if I lock the door, that full professor cannot come in here and start to teach. And so, what I do is I disable interrupts, and I keep the full professor from coming in by, I don't know, throwing chains around the door or something like that, all right? That is an example of setting priority. Oh, there's somebody right outside the window. I thought it was a full professor. That is an example of a interrupt and priority. So, I'm thinking, what is some good stuff I can just show you pictures of? Let's take a good picture of what you might find inside of our processor. Well, let's take a look all the way down here. And this is in the book, page 40, I believe. And remember I told you about how you can transfer information from one place to another. And oh my gosh, look at this. There's an example right here. Here is my direct memory access controller. And it is able to handle transfer, for example, from a ROM to a RAM. And it uses a different part of communications from the CPU. So I can continue using the CPU and do some other things and not have to worry about conflicting between the ROM and the RAM. But also notice that we have all, and here is here's the data flash up here as an example. So you can transfer from the data flash through the DMA over here to the ROM or to the RAM or something like that. And notice here that there are almost like 3 different data paths here that you can connect to with the CPU. So you can go directly from the CPU to the ROM, or you can go to the CPU and from that get onto this bus, and from that get onto any one of these devices. These devices out here are what we call our peripherals. And also notice this is where if you go to the external bus over here, you can get out to your ports. Now, are we going to dig into great detail about the computer architecture of this device? The answer is no. You just need to be aware that this stuff exists and how you would actually use it. And in fact, if you look really carefully, there's this little thing here that says internal main bus 1 to 6. Which implies that there's like 6 buses inside here. You can have stuff whipping all over the place. Who controls that? The hardware controls that. You don't actually have to worry about that. That's handled by the microcontroller's hardware. The little itty-bitty transistors inside of it. And that is the control path is handling this data path. So this is the data path. What are some other important things? Well, from your computer architecture, you know that your operations are done with an arithmetic logic unit. Our arithmetic and logic unit will take data from registers. And we look here, our registers say that they go from bit 0 to bit 31, 32 bits as we said. We also have an accumulator. And why were we so worried about that overflow operation when our accumulator is 64 bits wide? Well, very often we can organize our data such that we can use 2 registers to hold the result. And we would have to know that there's going to be a carry between these 2. When we work and write software in this class, do we have to worry about that? At this point, no. For us, that's a little bit too down low level for us to worry about in this class. We're going to be worried a little bit higher concept than that. By the way, if you remember, we work with a program counter that has the address of the next instruction to run. By the way, this is page 44 in our book. If we look further and say, how big are data items? And this is where I went earlier. A signed integer, 8-bit, is a character. A signed word, or a regular integer, is 16-bit, and a long word is 32-bit. And make sure you understand that. I am going to talk about floating point, and I'm going to be talking about endianness a little bit later. Oh, this is here's another concept. I just want to make sure you understand. Byte, word, long word in our device. All right. I will continue this conversation specifically about computer architecture in our next class. Thank you very much.